Welcome back. In today's lecture, we're going to talk about planetary atmospheres and focus on what sets the basic properties of an atmosphere of a planet, what sets the density profile, what sets the height of an atmosphere, and look at how that will vary as we change the strength of gravity, the composition of the planetary atmosphere, and the planet's temperature. In order to discuss planetary atmospheres, we're going to have to review some basic properties of gases and solids, begin by talking about the bulk property of materials. I think a lot of the material in that first section may be reviewed for many of you. We'll talk about pressure and density and temperature again. Then we'll turn to the atomic level and look at how these concepts of pressure and temperature could be understood at the atomic and molecular level. And then finally, we're going to apply the idea of hydrostatic equilibrium, that an atmosphere is in balance with gravity pushing down and the pressure gradient pushing up, and these two forces are in equilibrium, and that equilibrium determines the basic properties of an atmosphere of a planet. As we'll see later in the course, this same balance between gravity and pressure will also determine the basic properties of stars. So let's begin by reminding ourselves of the bulk properties of matter. The different states that we will encounter in this course are solids, good description of the crust, say, of the Earth, liquids, like our ocean, gases, like our atmosphere, but we'll also encounter plasmas. A plasma you can think of as an ionized gas. If you have hydrogen atoms or molecules, that's in a gaseous form. The hydrogen atoms and molecules are neutral, with electrons orbiting around each of the protons. A plasma is ionized. It's made up of free protons and free electrons, and the two move independently. And plasmas, which actually make up most of the visible universe, most of the volume is filled with plasmas, actually have richer behavior than gases do, because magnetic fields play a very important role in determining the dynamics of plasmas. But let's just remind ourselves of the properties of solids, liquids, and gases. Solids are organized often like crystals, with lots of long-range order. Gases consists of atoms or molecules basically moving randomly. There's no pattern or order in a gas. Liquids lie in between. There's some local order, but on the large scale, the molecules and atoms move freely. Of course, in their bulk form, we're familiar with the basic states of water. Ice is a solid, liquid water, and then steam as a gas. When we talk about the bulk properties of materials, we'll talk primarily about the density of materials. We'll sometimes talk about the number density, though that really requires the concepts of atoms and molecules, so we'll actually defer that to the second section of our discussion. We've already talked about temperature. We're going to talk a lot about pressure, and we also need to concern ourselves about the composition of the gas. When we look at atmospheres of planets, we'll often look at atmospheres whose compositions are made up of things like carbon dioxide, oxygen, methane, nitrogen, and hydrogen. And when we look at planets, we're going to encounter materials where we'll see a range of densities. When we look at solids, the characteristic density to think about is the density of water. It's a gram per cubic centimeter. Iron is about 8 times larger. Quartz, so of a characteristic density for the crust of the Earth, about 2 to 3 times higher. We're dealing with the crustal materials. And air is much less dense than a solid. A characteristic density for a solid is a few grams per cubic centimeter. Well, the air in this room has a density of more than 1,000 times smaller, a density of about 0.001, 0.013 grams per cubic centimeter. When we're dealing with these densities, it's actually a little more convenient not to work with grams and centimeters, but kilograms and cubic meters. And an easy number to remember is that the density of air in this room is roughly a kilogram per cubic meter. It's actually a little bit more, about 1.3 kilograms per cubic meter. A concept that we're going to make a lot of use of in this lecture is pressure. think we're all roughly familiar with pressure in daily life. If I have a bike tire under high pressure and I open it up, the air will flow out. Air will always flow from regions of high pressure to low pressure. You can think of an engine operating where you've got lots of hot gas here under high pressure pushing upwards. And we could relate the pressure to the force exerted, that this gas pressure will exert a force proportional to the area. So pressure is equal to force divided by area. This is why stiletto shoes can do so much damage to a floor. Stiletto shoes, you've got a lot of force here, the whole weight of the person standing in those shoes, and that force is concentrated on a very small area that exerts a tremendous pressure downwards and will poke holes in the ground. This is why some buildings forbid shoes like that shown here. One of the most important relations we're going to use when we talk about atmospheres is the ideal gas law. In the bulk form, the key idea is pressure is proportional to density times temperature, so that you can have high pressure by either having high temperature or high density. It's the product of these two. This term here, this constant, is a constant that depends on the material and is just a constant number, and when we start to look at the atomic level, this will make even more sense. Often when we're dealing with equilibrium situations where there's not rapid change, the atmosphere is isobaric or at constant pressure. If things aren't isobaric, we have a variation in pressure. That's going to drive a wind. And on our planet and other planets, winds will flow from high pressure regions to low pressure regions. We can have constant pressure often by balancing things like low density and high temperature against high temperature and high density and low temperature. So as long as the product of these two are the same, the pressure will be constant. Another thing that we encounter when we look at bulk properties of matter is heat flow. If we have a hot region and a cold region next to each other, put some ice in hot water, the ice will melt. Heat will flow from high temperature regions to low temperature regions. And there's three important ways in which energy flows that we'll encounter in astrophysical environments. We've already talked about radiation. We've already talked about how the sun radiates its heat, and the energy radiated from the sun heats the Earth, and how that's in balance with the Earth itself radiating in the infrared. Radiation means that the energy is carried outward by light, by photons, by optical photons primarily from the sun, infrared photons from planets like Earth and Mars. Conduction is when the heat is carried by electrons. If you have a piece of metal, you heat one end, the electrons will move along that metal and carry energy with them. And metals are very good conductors. On the other hand, materials that are insulators, like this glove here, is a poor conductor, which is why you can touch this piece of metal with the glove, but would want to touch it with your bare hands. So insulators are poor conductors, while metals will be good conductors. And finally, there's convection. With convection, there's bulk motion of the gas. So if you have convective heating, the air flows upwards, carrying heat with it. And it's the motion of air that transfers energy. So those are the basic ideas we want to talk about when we talk about bulk properties of materials. Next, I'd like you to make some rough estimates of characteristic densities that we encounter in astrophysics and estimate the density of the Earth and the density of the Sun, and then come back and we'll talk about the properties of atoms.